In this video, I am going to discuss geometrical isomerism. So, what is the exact definition of geometrical isomerism? What is the meaning of geometrical center? And what are the various examples of geometrical centers? So, first let us take the exact definition of geometrical isomers. So, here geometrical isomers or geometrical isomerism is a type of configurational isomerism. You already know the meaning of a configurational isomerism. So, geometrical isomerism is basically a configurational isomerism, and this is due to restricted rotation of atoms or groups. You already know rotatable bonds and non-rotatable bonds, flexible bonds and rigid bonds. This geometrical isomerism is due to restricted rotation of atoms or groups around a double bonded system or cyclic system. So basically, geometrical isomerism is configurational isomerism, non-interconvertible stereoisomers, and this isomerism is due to restricted rotation. That means the molecule has rigid bond. Due to the presence of a rigid bond, there will be restricted rotation, and due to this restricted rotation, geometrical isomerism is possible, and restricted rotation is particularly in case of double bonded system and ring system. For example, let us understand this is molecule 1 and this is molecule 2. If you carefully observe, these two have same molecular formula, same structural formula, but here there is a CC double bond. Due to that particular reason, there is no free rotation. So this is the rigid bond. So due to rigidity around this particular bond, free rotation is not possible. Because of that, these two molecules exist independently. This cannot be converted into this. If you see the relation between the first one and second one, you can see hydrogens are same side to the double bond and hydrogens are opposite side to the double bond. And this is the minimum distance between two hydrogen atoms, and this is the minimum distance between two hydrogen atoms. If I say this distance is L1 and this distance is L2, no doubt L2 is greater than L1. These two are having some relation. These two are having a relation of configurational isomers, and particularly this isomerism is due to the presence of rigid bond. Whenever configurational isomerism is due to the presence of rigid bond, then those isomers are called geometrical isomers. So these two are geometrical isomers. You can take another example. So these are the two compounds which are having the same molecular formula, same structural formula, but if you see the spatial orientation, at this carbon methyl group is above, at this carbon methyl group is below. So this cannot be converted to this. There is no interconversion because the molecule has rigidity. Due to rigidity, there will be restricted rotation. Due to that restricted rotation, this one and this one exist independently. And if you see the distance between two methyl groups, this is if I say L1, here the distance between two methyl groups, that is L2, L1 and L2, if you compare, no doubt L2 is greater than L1. So the spatial orientation is different. Here in the first example, methyl groups are same side to the planar ring. Here methyl groups are opposite side. Even you can observe one more example. Here the two molecules given, these two molecules are having the same molecular formula, same structural formula. Most of the students, when they are learning first time, if anyone asks what is the relation between these two, immediately they say they are positional isomers, which is incorrect. They are not positional isomers. Here the numbering should be started from this place, here numbering should be started from this place. So that is double bond position is 1 only. So they are not actually positional isomers, they are not structural isomers, they are stereo isomers. And if you see here, the hydrogen is like this, here the hydrogen is like this, and here you can see hydrogen and here hydrogen. In the first example, due to the presence of double bond. In the first example, two hydrogens are opposite side to the double bond, two hydrogens are same side to the double bond, and due to the presence of double bond, due to the presence of ring system, there is no free rotation, so this cannot be converted to this. Because of that reason, these two exist independently, and the relation between these two compounds, they are said to be geometrical isomers. One more example to understand the definition of geometrical isomerism. So this is molecule 1 and this is molecule 2. They have same molecular formula, same connectivity, but in the first one, if you see, hydrogen and OH are same side to the double bond, and here hydrogen and OH are opposite side. Due to the presence of a pi bond perpendicular to sigma bond, there is no free rotation. Due to the absence of a free rotation or due to rigidity, first molecule cannot be converted to second molecule. So these are non-interconvertible stereoisomers. Non-interconvertible stereoisomers are configurational isomers, and these two configurational isomers are particularly due to the presence of rigidity present in the molecule, hence these are called geometrical isomers. So this is about a definition of geometrical isomerism. Now let us take the exact meaning of geometrical center. Geometrical center is the term we are using only to understand whether the given molecule shows geometrical isomerism or not. Even after completion of all geometrical isomerism examples, we will be calculating how many geometrical isomers are possible for the given structure. In that situation, this geometrical center term will be very much helpful. So here geometrical center which is responsible for geometrical isomerism. It is the center which is responsible for geometrical isomers or geometrical isomerism. You already know geometrical isomerism is due to rigidity. So particularly the rigidity is due to double bond, and also that is due to ring system. So obviously this geometrical center can be double bonded system. It can be CC double bond, CN double bond, or CO double bond, or even NN double bond also. Even cyclic structure that is ring system is also responsible for geometrical isomerism. Therefore, this CC double bond, CN double bond, any double bond or any ring system is said to be geometrical center. If you see the examples of geometrical centers, the first one, that is a double bond. Yes, it can be CC double bond, CN double bond, CO double bond, NN double bond. Single bond in ring system, that is also rigid bond. Cumulin system, we will discuss in detail what is cumulin, how cumulin is produced. Spirane system, that is also one of the examples of geometrical centers. Even polyphenol system. So these are the examples of geometrical centers. Whenever the molecule contains any one of these geometrical centers, there is a possibility for showing geometrical isomerism. Now let us discuss geometrical isomerism in alkenes. In case of alkenes, you already know there is C double bond, and this is responsible for the rigidity. Due to the presence of rigid bond, alkenes can exhibit geometrical isomerism. But the further condition is the two groups or atoms attached to single bonds of sp2 carbon must be different. For example, this is alkene system. This is sp2 carbon. This is also sp2 carbon. These are the single bonds of sp2 carbon. The condition is the two groups or atoms attached to the single bonds of sp2 carbon must be different. Here we have hydrogen, here also we have hydrogen. The condition is not satisfied. Actually, there are two sp2 carbons. At both the carbons, the condition must be satisfied. Here the groups attached to single bonds, one is methyl group, another one is chlorine. Here the condition is satisfied, but here the condition is not satisfied. Therefore, this alkene does not show geometrical isomerism. Again you see this is sp2 carbon, this is also sp2 carbon, and these are the single bonds of sp2 carbons. Here we have ethyl group, here we have hydrogen, here the condition is satisfied, but here the condition is not satisfied, therefore geometrical isomerism is not possible. Next example you see this is sp2 carbon, sp2 carbon, here we have hydrogen, here also we have hydrogen, the condition is not satisfied, geometrical isomerism is not possible. Even in the next example, here methyl groups are repeated, therefore geometrical isomerism is not possible. For example, which type of alkenes exhibit geometrical isomerism? If you see the three types of alkenes, I will be reading these alkenes as AB structure. AB groups of first double bonded carbon, AB groups of second double bonded carbon. I will read it like this: AB type of structure, AD type of structure, ABDE type of structure. Now if you see here, AB condition is satisfied, AB here also condition is satisfied, so this molecule shows geometrical isomerism. Here we have A, here we have D, so here condition is satisfied, A, B, two different groups, here also condition is satisfied, so the molecule shows geometrical isomerism. And if you see the third example, the groups are D and E, two different groups, here groups are A and B, two different groups, at both the sp2 carbons the condition is satisfied, therefore geometrical isomerism is definitely possible. So which type of alkenes exhibit geometrical isomerism? If you see the three types of alkenes exhibit geometrical isomerism: AB first category, ABAD second category, ABDE third category. These are the three types of alkenes exhibit geometrical isomerism. To represent geometrical isomers of alkenes, what are the two different configurations we can use? One configuration is cis-trans system, another one is EZ system. First let us take a cis-trans system. In case of a cis-trans system, it is very simple. If there is at least one common group, here you see the two double bonded carbons, here A, B, two double bonded carbons have two common groups, A, but here one is B, another one is D, only one common group. Cis-trans nomenclature is used whenever there is at least one common group. There must be at least one common group. So what are the possibilities? AB, AD. In these two examples we use cis-trans nomenclature. And cis isomer and trans isomer, if you see, if the common groups are same side to the double bond, here common groups are same side to the double bond, therefore it is said to be cis isomer. If common groups are opposite side to the double bond, then it is a trans isomer. So cis-trans isomerism is particularly used whenever the two double bonded carbons have at least one common group. If the common groups of two double bonded carbons are same side, cis isomer, opposite side, trans isomer. So let us take some examples. Here geometrical isomerism, first question, geometrical isomerism is possible or not? If possible, whether it is a cis-trans configuration or EZ. If it is a cis-trans, whether it is a cis isomer or trans isomer, these are the three things you need to answer. So chlorine, hydrogen. So geometrical isomerism is possible, and there are common groups, and here common groups are chlorines, otherwise hydrogens, they are same side, therefore it is a cis isomer. A geometrical isomerism is possible, common groups are opposite side, therefore it is said to be trans isomer. Again, there are common groups, you can see this is AB type of structure, COOH groups are same side, hydrogens are also same side, therefore this is a cis, its common name is malic acid. Here COOH and here COOH otherwise hydrogen and hydrogen, their opposite side, therefore it is a trans. That molecule is said to possess trans configuration. But if you see the next example, this is A, this is B, this is A, this is D, only one common group, and those common groups are hydrogens. Hydrogens are same side, therefore it is cis. Hydrogens are opposite side, therefore it is a trans. Now let us discuss the second configuration of alkenes. In order to represent geometrical isomerism, we use cis trans and EZ. Now we are discussing EZ system. Here we need to answer when to follow this system, how to follow this system, what are E and Z. Under 3 questions, I will be completing this EZ system of configuration. This EZ system of configuration is used when there is no common group. So this is one double bonded carbon, here this is also one double bonded carbon, here the groups are A and B, here the groups are D and E. The two double bonded carbons or two sp2 carbons do not have common group. Whenever common groups are absent, in that situation we have to represent a geometrical isomers of such alkenes by using EZ system of configuration. How to follow this EZ system? You have to apply this particular configuration in 2 steps. In the first step, you have to give the priorities to the 2 groups of one double bonded carbon by using CIP rules. So in the first step, what you have to do is, so these are the 2 groups of first sp2 carbon, these are the 2 groups of second sp2 carbon. We have to give the priority to these 2 groups based on CIP rules, like 1 and 2 we have to give the priority 1 and 2. Even we have to apply CIP rules to give the priority to the 2 groups of another sp2 carbon. Here also we have to assign the priority as 1 and 2. That is the first step. So each double bonded carbon, the 2 groups of each double bonded carbon are assigned 1 and 2 numbers, and this is completely based on CIP rules. This is step 1. After that, you just check if high priority groups or low priority groups, if they are same side. If high priority groups are same side, by default low priority groups are also same side. In that situation, we have to say that particular alkene is said to possess Z configuration. If high priority groups are opposite side, if high priority groups are opposite side, by default low priority groups are also opposite side. In that situation, the molecule is said to possess E configuration. Now let us take what are E and Z. Here E is antagon, which means opposite. Z is jusamin, which means same side, together, otherwise same side. If high priority groups are opposite side or low priority groups are opposite side, then we have to use the configuration E. If they are same side, then we have to use the configuration Z. And I'll give one hint to remember, because most of the students are getting confused. Cis and trans, okay, but E and Z, they are getting confused. So what is the mnemonic I am going to give to remember this EZ configuration? In case of a same side, instead of S you write a same. So here if they are same side, then you have to use the Z. Opposite side, opposite side. So here instead of O you write a E. Now you read this, and obviously if they are like this, the configuration is E. If they are like this, the configuration is Z. So mnemonic words: same, opposite. This is about EZ configuration of alkenes.